Here is yet another related rates problem. We have a car and a tractor traveling on perpendicular roads. When the car traveling east at 50 miles per hour leaves the intersection of the two roads. Okay, so oops, let's see here. We've got the two roads. So the car is traveling east at 50 miles per hour, so it's headed this way. There's a car and a tractor traveling. The tractor is 2 miles south of the intersection, traveling north at 20 miles per hour. So okay, so the tractor's down here going that way. The question is, how fast is the distance between them changing when the tractor is only 1 mile from the intersection? Okay, so I'm going to put the car somewhere out here and the tractor somewhere here. I mean, I know initially the car is here, but then it moves, and the tractor is initially somewhere down here, and then it moves upwards. So they give me the speed of the car, 50 miles per hour. 50 miles per hour, that's speed, that's a change in distance. So why don't I make this distance right here be, I'll call it x. It's the distance from the intersection to wherever the car is, and that's going to change as time changes, but the rate at which it's changing is 50 miles per hour. So this is x equals 50 miles per hour. So it isn't, it's dx dt. It's the rate of change in x. X is the distance, 50 miles per hour is the rate of change. Okay. Likewise, I'm going to call this distance right here y, and this will be the distance the tractor is from the intersection. Right? So dy dt, the rate of change here is, what do we say, 20 miles per hour. But actually, it's not 20 miles per hour because y is getting smaller. The tractor is actually approaching the intersection, traveling toward the intersection. So let's make dy dt negative because y is getting smaller. Okay. The question is asking, how fast is the distance between them changing? So let's call that z. Okay. The question is, what is dz dt? This is when y equals 1. Okay. So related rate problems are all similar, right? They all give you one rate, they ask for another rate. Well, this one gave you 2 rates and asked for another rate. So what we need to do now is we need to find a relationship between x, y, and z that's always true. Well, perhaps you can see that in this situation here, no matter where the car is, no matter where the tractor is, you've got a right triangle, and hence Pythagoras. Pythagoras is always true here. X squared plus y squared equals z squared. Okay. There's a relationship between the variables involved. Now we can implicitly differentiate with respect to t to find the relationship between the rates involved, right? Each one of these things, x, y, and z, are changing as time changes, right? So I don't want to plug in any numbers yet. I don't want to treat any of them as constants. They're all variables. They're all changing with time. So implicitly differentiating with respect to t, the derivative of x squared with respect to t is 2x times dx dt, plus the derivative of 2y, which is 2y times dy dt, equals the derivative of z squared, which is 2z dz dt. Now I have a relationship between the rates dx dt, dy dt, and dz dt. So I'm going to actually, I'm going to divide by 2, and then I'm going to plug in everything I know and solve for the one I don't. So I'm going to divide by 2 first. X times dx dt plus y times dy dt equals z times dz dt. Okay. Now, the thing that I'm looking for is dz dt, so I better be able to find everything else somehow. Okay. So let's go. We've got, well, I've got y equals 1. I know dx dt, I know dy dt. I got to figure out what y and z are. Well, Okay, I got to do a little bit of work on the side here. When y is 1, all right, we were traveling at 20 miles per hour. It started off at a distance, the tractor, 2 miles south. So the tractor was 2 miles south of the intersection. I want to know when it's 1 mile south. So it's traveled 1 mile at 20 miles an hour. How long does that take? So 1 mile equals rate times time. So 20 times t. So t is equal to 1 divided by 20, which is 0.05. I think. Yeah. So, well, I could just leave it as 1 divided by 20, right? It's 1/20th of an hour. Well, now, how far did the car go? Because that's going to tell me what x is. In that 1/20th of an hour, if I take the 50 miles per hour and multiply it by 1 over 20, sorry, I've got 5 halves, or 2.5 miles, right? So 2.5 miles is what x is equal to when the tractor is only a mile away. So, all right, so the x is 2.5, dx dt is 50, plus y, which is 1, times dy dt, which is negative 20, equals z. Do I know what z is? Well, I know this is 1, and now this is 2.5, so I'm essentially using this relationship here to get that this is the square root of 1 plus 6.25. So z is the square root of 7.25 times dz dt. Okay. This took a little extra work here because I had to use various relationships that were given to figure out what each of the pieces were. I'm down now to only not knowing what dz dt is, and so I can solve for dz dt. So I've got, let's put this stuff together. I've got 2.5 times 50 minus 20, so that's 105, divided by the square root of 7.25 is dz dt, and that's equal to 38.996. And this would be miles per hour. Okay. A little bit different, only because they gave us 2 rates and asked for a third. Right? We still needed a relationship between the variables x, y, and z, all the stuff that's changing. This is, even though x, y, and z are changing in length, the Pythagorean theorem is always true. And so then when I differentiate with respect to t, I get a relationship between the rates, dx dt, dy dc, and dz dt. Plug in everything I know. Maybe I got to do a little work to get everything I know. But solve for the rate that's unknown, and we've got it. Okay. There you go.